All right, I'm worried this is going to be a long one, but let's see what we can do. So go ahead and copy this stuff down. So a sequence is just a list of numbers. So if you look down here, I've got a sequence right here. It's just a list of numbers, usually with a pattern or a function rule. So you can see I've got like a rule for the sequence down here. I'll let you copy that later. We use a letter and a subscript to refer to the terms of a sequence. So that's an example of letter and subscript. That's an A4 at the bottom. I know my writing is a little bit messier on this iPad with the, it's not actually an iPencil or whatever it's called, but it's a crayon. Okay, so if the function rule for a sequence is f of n equals 3n, so we talked about a function rule, we can write out the terms just by plugging in 1, 2, 3, 4 and finding a pattern. So the first term is a sub 1, the second term is a sub 2, the third term is a sub 3, and so on. Other common letters used for sequence are B, so like B sub 1, B sub 2, B sub 3, etc. And S. Those are pretty common letters used for sequences. So all I'm doing to find the terms is plugging in a 1 and then a 2 and then a 3 and then a 4 into the function rule, and we can write the sequence like that. So go ahead and copy the rest of that down. And then the 3n is called the nth term. So we have first term, second term, third term, fourth term, dot, dot, dot. And then the general term, oops, that's an M. The general term is the nth term, okay? So write the nth term for these sequences, also known as the function rule. So we want to write something that looks like this, the function rule or the nth term. So what I suggest is you get comfortable with both recognizing the notation for the term itself. This is a sub 1, this is a sub 2, and so on. And then realize that this was achieved, or we got that first term by plugging one into something. Here we plugged 2 into something. Here we plugged 3 into something, and here we plugged 4 into something. So we need to figure out what that thing is. So start piece by piece. They all have a numerator. They all have a first term of the they all have a first factor of the denominator and a second factor of the denominator. So ask yourself, what do you notice about the numerator? So hopefully you said, the numerator is always 1. That's easy. Every single fraction, the numerator is always 1. Then look at the denominator and the first factor. So I'm going to color code this. I don't know what colors I haven't used. The first factor, how does that connect to the n value? Well, it's n itself. N equals 1, n equals 2, n equals 3, and so on. Then we want to look at the second factor and ask, how does that connect to n? Well, each of those is 1 more than n, so that's going to come from that. So this is really a pattern recognition thing. I don't even know what else to call it besides a thing. And this goes back to, it's really either our mind recognizes patterns easily or we have to work at it a little bit harder. And it also, the more you practice recognizing patterns, the easier it gets. Okay? All right, so let's look at this one. Again, we want to focus on the numerator separate from the denominator. We're going to write a function rule, and we want to notice, so let me go back to my yellow. This came from plugging in 1 into something, 2, 3, 4, This is a sub 1. The term itself is a sub 1, a sub 2, a sub 3, and a sub 4. So I'm trying to make this distinction. If I were listing out the terms like this, I would do something like this. I don't want to write another one because it's taking up time that I think is unnecessary. But the idea that I achieved this term by plugging in 1 and so on and so forth is what I want you to get. So let's focus on the numerator. I see a 2 and a 4 and an 8 and a 16. So again, pattern recognition. I don't have a trick for this one. So hopefully you identify that these are all powers of 2. If I plug in a 1 into 2, or if I raise 2 to the first power, raise 2 to the second power, raise 2 to the third power, and so on, I end up with the numerator of each of those fractions. And this is a super common pattern or super common type of sequence. Now I want to focus on the denominator. So I need to think 3, 9, 27, 81. Hopefully you see that pattern of multiplication, which means it's an exponential function. Raise 3 to the first, 3 to the second, 3 to the third, 3 to the fourth. So we have 3 to the n. So we're going to write the general function rule just a little bit simplified, like that. Okay. All right. So last one of these. When there's an alternating negative, or even just a negative in general, even if it's on every term, I would suggest focusing on the number part first and then worry about the negative. Okay. So remember, this is our first term, our second term. We label them with that. We got this term by plugging 1 into something. And we got this term by plugging 2 into something, and 3, and 4, and 5. So what happens to go from 1 to 2? I am given a plug-in 1 and I end up with a 2. Well, there's two things that could happen. 1 times 2 or 1 plus 1. So if I'm looking at the first term, I'm analyzing the first term. I know I'm plugging in a 1 and I want to get out a 2. So there's two ways to do that. I can take that initial 1 and multiply it by 2, or I can take that initial 1 and add another 1. Now I want to see which of these two patterns holds for the other numbers. So if I'm analyzing a 2, I'm plugging in a 2 and I'm getting out a 4. We're going to focus only on the number part. We'll deal with the negative in a minute. Well, if I do the n value, let me color code this. The n value times 2 or plus 1. The rule has to stay the same. This is the rule. That has to stay the same. That's the function rule, right? Well, this is the one that matches this one, right? I don't get a 4 out of that function rule. So and then check it for the rest of them. Whoa, I just switched up the notes on accident. Okay, check it for the rest of them. 3 times 2 equals 6, 4 times 2 equals 8, 5 times 2 equals 10. So I know my function rule is going to have to do with multiplying the n value by 2. Okay, now I need to figure out how to get an alternating negative. And there's really only one way to do it. Well, two ways depending on if my first term is negative or my second term is negative. I need to have a negative. I'm not sure why I left that space in the front. I don't want to put that in the front. I didn't leave enough space to put it in the front. So I need to have a negative 1 raised to a power. It's always going to be, you have options. It's either n plus 1, or n minus 1, and you just have to figure out what it is. So let's start with n. If I raise, I don't have enough space here. If I raise -1 to the first, I get -1, and this term is not negative. So I know it's not going to be the n power. Let's write this as like n power. N plus 1 power, let's see what happens. If I plug in a 1, I have -1 to the n plus 1, which is -1 squared, and that works. That's positive. Now let's try it for n equals 2. -1 plugging in a 2 is -1 to the third, and that's negative, so that works here. And then you'll see that it's going to alternate because you're going to go from even to odd to even to odd. The same thing will be true of n minus 1. I don't have space to show you, but you can check it yourself. So I'm going to write, squeeze it in there. I'm going to write it just a little bit neater. Times 2 then. Maybe put a little multiplication sign. Since there's a space there, I don't want it to look like those are, the 2n is just floating in outer space. So again, another thing that you just kind of have to practice with. All right, recursive. So go ahead and copy that down. So another way of defining a sequence is recursively. So we're not using a function rule. We assign a value to the first term or the first few terms. We're only doing problems this year that involve assigning a value to the first term. Just one of the ways to simplify it because we're not learning in a normal environment. Assigning a value to the first 2 or 3 terms is not that much different, but again, I just want to keep it a little more simple this year. And then we state a formula for the nth term that uses those given values. So instead of talking about it in the abstract, let's do it. So if I'm going to write out my sequence, I'm going to have my answer over here. I'm already going to write my answer box. They already told me the first term is 3. Then I'm going to use that given term to find the next terms. So this formula right here, if I'm finding for n equals 2 now, the second term, I'm going to be finding a sub 2. So if I plug in, you won't need to write this out in so many steps in the like every time you do this, but just plugging in a 2 for both of these n's. Well, this tells me that a sub 2 is 4 minus a sub 1. And they told me what a sub 1 was. So that's what it's talking about here. We assign the value to the first term, and then state a formula for the nth term that uses those given values. So I'm using the a sub 1, plugging it in, and I get that a sub 2 is 1. So the second term, right? So this is a sub 1, this is a sub 2. What is it asking me to find? The first 5. So I'm not going to show this much work for the rest of them. So let me move over a little so I have more space. For n equals 3, whoops. For n equals 3, I'm going to say a3 is 4 minus, I'll show this step a little bit one more time. Again, I'm plugging in the n equals 3 into both of these n's here. So a3 is 4 minus a2. So a3 is 4 minus 1, which is 3. a4, a5, that's a 3. Sorry, that's an ugly 3, but that's a 3. So I took this a sub 2 and I plugged it in right here, and I got 4 minus 1 is 3. So let's see if we can be a little more efficient for the next. N equals 4. A sub 4 is going to be 4 minus a sub 3. And you might now see an alternating pattern, so you can probably guess. But if you want to be extra safe, double check it. And see that it's 3. Okay? So let's do one more. Hopefully I didn't scroll away from that too soon, but if I did, go ahead and rewind. So again, I'm going to be like, okay, this is my answer box, my A1, my A2, my A3, my A4, my A5. I already know my A1. I'm going to find my A2. by plugging in, I'll show it one more time here. Well, A2 is just the opposite of A1. So if I'm going to go and do what I did before, I'm going to plug this 2 in right here and then keep the rest of the formula the same. So that's -2. And then you probably don't need to do any more. Once you realize that it's just the opposite, you're like, oh, well, that's the opposite of A2. And oh, that's the opposite, the opposite of A3. So it's just going to alternate like that. Okay? All right, so go ahead and copy that. In many future math classes, we look at properties of sums. Sorry, that's a funny S. Sums of sequences. So this is a big topic in Calc BC. So instead of listing A1, comma, A2, comma, A3, etc., we're actually adding the terms together. So instead of writing the sum the long way, we use summation notation. It looks super scary and overwhelming. It's not that bad, okay? Trust me. So these two things are equivalent at the top of the page. Okay. The weird looking E thing is a Greek letter called sigma. You might recognize it if you've ever watched a movie that involved fraternities or anything like that. The K is called the index. J is another very common index, as well as I. And the bottom underneath the sigma tells me where to start, and the top tells me where to end. So let's just demystify this, okay? This looks all scary, but let's just demystify this. This is telling me I'm going to start by plugging in k equals 0. And I'm going to plug in k equals 1. And k equals 2. And usually 3 terms is enough to find a pattern, okay? 3 terms is enough to find a pattern. So then this is telling me to stop when, I don't know why I put a parenthesis there. This is telling me to stop when k equals n minus 1. So I'm going to plug in an n minus 1 and simplify it to get that. So the way that I would write the sum, I'm going from the short notation, which is summation notation, to the long notation, which is writing out the sum. I would go like that. And I would probably put that in parentheses to make it clear that that's together, that's all one term. This is just adding up odd numbers, 1, 3, 5, 7, 9, blah, 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 until I get to whatever the n value is that they want me to stop at. So right now I'm leaving it generic, because this is telling me to leave it generic. That could be a number, and then it wouldn't be generic. We'll get to that in a bit. Okay, moving on. Express each sum using summation notation. So this is back to the pattern recognition, except that the pattern is really given to you. This is your A sub n term. Okay, so can you tell what's going on here? There's your n right there. You do need to verify it, because what if they decided to be weird and put n times 12? I mean, they wouldn't do that. That's not convention. Math convention is that the coefficient goes in front of the n, so 2n makes more sense than n times 12. So let's check it. This is n equals 1. A1 by my formula that I just created would be 1, and that matches. This is n equals 2. A2 by the formula that I just created would be 3, and that matches. And you can keep going if you want, but I think you probably feel pretty confident with that. So this one is going the opposite direction. The starting point, we just plugged in a 1. That's how we're going to know the starting point. We're going to use the index of k, just because that's what we used up here, okay? We're going to use the index of k. Starting point is k equals 1. Ending point is k equals 12. And you don't have to write the k equals on the top. You'll see up here, there it's not k equals on the top. It's just the ending point, okay? So this is an example of where it's numeric. And then instead of generic. 2k minus 1 is our formula. We're plugging in k equals 1 up to k equals 12 into the formula 2k minus 1. Why does it switch from n to k? Because math likes to be difficult. I don't have a better answer. I don't have a better answer than that for you. So again, here is your formula. If I was talking about this in terms of a sequence instead of a sum, I would say this. Since I'm talking about a sum, I'm going to use k or j or I, but the book pretty much sticks to k. And then I just have to figure out the starting point and the ending point. Double check that that's the formula just to be safe. I think mentally you can do that. Plugging in a 1, plugging in a 2, plugging in a 3, and so on, right? So this is clearly telling me that my starting point is k equals 1. My ending point is k equals n. The last thing I plug in to get that last term is n. So again, pattern recognition really comes from practice. All right, last thing. I feel like this video is so long and I apologize, but it's just there's so much in this chapter. So go ahead and copy that. The details on page 804, there is one property that I'm ignoring. I'm just keeping it simple. It's the fourth one. There's like a box with these three and it has a fourth one. By the way, these are B's and I'm looking and seeing that they look like 6s. These are B's, okay? There's no 6s, not a single 6. Well, actually that's not true. This is a 6, but I think that actually looks like a 6. So when you look at the properties when you review the details on page 804, there's a fourth one and we're ignoring it. And then these 4 down here are in their separate box. So you'll see what I mean when you actually look at the pages. All right, so this looks scary and abstract and freaky. I'm not gonna talk about them in the abstract. Let's just put them into action, okay? So what I see here is I have a coefficient and a variable. So I want to look up at these properties and figure out where there is a coefficient and a variable on the left side. Well, coefficient and variable, or function rule, however you want to, something with a function rule. So what this is telling me is I can pull the coefficient out in front and then find the sum of the thing that involves the variable. So I'm going to pull that -1 out in front, and then I've got that. Well, now I just have the sum of k. Oh, look at that. That's the formula for the sum of k. So I'm going to use that formula to replace this right here, noticing that n is 24 in my problem. Okay, so the negative is going to hang on for the ride. Then the formula is going to be, I'm going to see if I can color code this. I'm going to put the 24 in for both of the n's, and everything surrounding is going to stay the same. And then I just have to do the math. I literally am just plugging 24 into that formula. So 24 times 25, I am not feeling like, let's see, 4 25s is 100 and I have 6, so 600, right? 600. Hopefully you followed that. If not, just multiply it out. So I have 600 over 2, so my answer is -300. As opposed to writing out 24 terms. -1, -2, -3, -4, minus ... all the way up to -24. That's what this sum would look like. And I would have to do all of that subtraction. Instead, I have a formula. And yes, you do have to I'm going to say work on memorizing these formulas, and I will think before we have an assessment on this whether I'm going to give them to you or not, but I would say work on memorizing them, okay? All right, woo, last one. Oh, no, 2 more. I thought we were on the last one. Okay, so now on this one, I see that I have subtraction. That's the first thing that I'm noticing. So I want to look up here. Where do I have subtraction? Right here. So this tells me I can split it up into two separate sums. So I'm going to go sum, first thing, minus sum, second thing. Now I have the same thing I had in 5a, where I can pull that coefficient out in front. And then I'm going to use that same formula that I used, where I'm plugging in the 26. One of my favorite classes during my master's used these formulas. I don't even remember what we used them for, but I guess I'm a little bit of a nerd. I really enjoyed it. So the sum of a constant, okay, that doesn't involve a variable, right? That's a constant. So let's look and see, where do we have the sum of a constant by itself? So see if you can find it. So this one is 5b, and this one is telling me to just multiply this number times this number, right? So let's look here. I'm going to multiply. Sorry, I'm changing my colors. I'm getting a little obsessive with the color coding here. 26 times 7. Multiply this number times this number. Okay? So I'm going to have, I wish I had a calculator close by, but whatever, I know how to math. 26 times 27, that's 42, that's 14, so 18, that's 12. Watch me make a mistake. Wouldn't that be funny? That's 5, that's 702. And then 26 times 7. $182. Oh, I just did that already, didn't I? Duh. Could have just stole it from there. 702, let's see, 700 would be 350, so 351. Oh, yeah. And then 3, I'm not mathing in my head right now. 315, 1053. Minus 182. $871. Okay. I didn't get a lot of sleep last night, so if my arithmetic is wrong, don't laugh at me. All right. If my arithmetic is wrong, I have every confidence that you guys will figure out the right answer and maybe share it in class or something. You can laugh at me, just don't tell me you laughed at me. All right, very last one. Is this like a decade long? I don't even know. When I'm recording this way, it doesn't show me how long I've been recording. Okay, we're going to do the same thing we did in 5b with the difference. That one's a difference, not a sum, right? Yes. So we're going to split it up. And you might be comfortable doing 2 steps in one here. You might jump straight to this in your first step, and that's totally fine. My sigmas are getting very messy. So now we have a new formula for k squared. Oops, why did I write it like that? Told you I didn't get much sleep last night. That one's for 5c. So flip back to that in your notes because I'm going to scroll past it. N times n plus 1 times 2n plus 1 over 6. Well, let me color code it. Let's see if I can figure out the spacing on this without writing. N times n plus 1 times 2n plus 1 over 6. Don't forget about that 2 hanging on for the ride. And then we already learned that the sum of a constant, we multiply these together. And I'm going to leave that arithmetic for you. It'll take you like 5 seconds to punch that into a calculator, and it will save us some time on the video. Okay? See you next time.